In this video, we'll talk about transmission media and how can we select the perfect one. First of all, what's transmission media? Well, transmission media enables computers to send and receive messages but do not guarantee that the messages will be understood. There are two main groups of transmission media, namely the guided medium and the wireless medium. For the guided medium, there is a physical path such as a cable for electromagnetic wave propagation. Wired media generally use a metallic or glass conductor that serves to conduct, or carry on, some form of electromagnetic energy. Twisted pair and coaxial cable systems, for example, conduct electrical energy, usually employing a copper medium. Fiber optic systems conduct light, or optical energy, generally using a glass conductor. The term guided media refers to the fact that the signal is contained within an enclosed physical path that guides the signal. For the wireless medium, however, the electromagnetic wave is transmitted through air, water, or vacuum. A wireless medium is also called an unguided medium. Rather than relying on electrical energy, such systems generally make use of radio waves, hence the term radiated often is applied to wireless transmission. Finally, wireless systems employ electromagnetic energy in the form of radio or light waves that are transmitted and received across space. Microwave, satellite, cellular, and a great number of special-purpose radio systems are wireless in nature. The selection of the most effective transmission system for a given application must be made in the context of a number of key design considerations. Such considerations include general transmission characteristics such as bandwidth and error performance, both of which affect throughput. Additionally, you must consider the allowable distance between devices as well as issues of propagation delay, security, mechanical strength, physical dimensions, and speed of deployment. Finally, and perhaps most importantly, consider local availability and cost. The basic transmission characteristics of a given medium are of primary importance. Those characteristics include bandwidth, error performance, and distance between network elements. These three dimensions of a transmission system, in combination, determine the effective throughput, or the amount of information you can put through, that is, sent over, the system. Bandwidth, in this context, refers to the raw amount of bandwidth, or capacity, the medium supports. Error performance refers to the number or percentage of errors introduced in the process of transmission. Distance refers to a minimum and maximum spatial separation between devices over a single link, rather than over a complete end-to-end circuit. Note that bandwidth, error performance, and distance are tightly interrelated. In a twisted pair network, for example, more raw bandwidth requires more raw material in the form of Hertz sine waves, which translates into higher transmission frequencies. Also note that radio systems are naturally limited in terms of bandwidth. Radio systems are highly sensitive to the quality of the atmosphere between the transmitter and the receiver. Dust, smoke, haze, and humidity have decidedly negative effects on signal performance. Other characteristic is propagation delay, and it refers to the length of time required for a signal to travel from transmitter to receiver across a transmission system. Factors impacting propagation delay include the distance between transmitter and receiver and the density of the medium. The speed of the electromagnetic signal depends on the density of the medium through which it travels. Clearly, the total length of the circuit directly impacts the length of time it takes for the signal to reach the receiver. The circuit length between 2 points can vary considerably in a switched network, as the specific circuit route can vary in length from call to call, depending on the availability of individual links that comprise an end-to-end circuit. Dedicated networks offer the advantage of a reliable and consistent level of propagation delay. In either case, the number of network elements in the network. Each device acts on the signal to perform certain process, security, addresses the protection of data from interception as it traverses the network. Mechanical strength applies especially to wired systems. Each type of wire, fiber, and cable has certain physical limits to the maximum severity of the bend it can tolerate without cracking or breaking, and the amount of bending and twisting. Physical dimensions. One must consider the shear weight of a cable system and the bulk, the size and weight of the reflective microwave or satellite dish and mounting system. Speed of deployment. Wired connections take some time. Even radio antennas may take some time to install, but once they are in place, the time required to configure and reconfigure the connections between them can take little time, if any. Cost. Cost considerations include acquisition, deployment, operation and maintenance, and upgrade or replacement. Now, I'll explain the characteristics of each of the following transmission media: twisted pair, coaxial cable, microwave radio, satellite radio, and fiber optics. Twisted pair involves two copper conductors, generally solid core. Each conductor is separately insulated by a dielectric material. The insulation separates the conductors so that the electrical circuit is not shorted and protects the conductors from physical damage. Bandwidth. The effective capacity of twisted pair cable depends on the gauge of the conductor, the frequency of the signal, the nature of the dielectric insulating material, the length of the circuit, and the spacing of the amplifiers/repeaters. Error performance. Twisted pair cable is especially susceptible to the impacts of outside interference. Security. UDP is an inherently insecure transmission medium. While it is relatively simple to place a physical tap on a UDP circuit, it also is fairly simple to detect the presence of a tap. Cost. The acquisition, deployment, and rearrangement costs of UTP are very low, at least in inside wire applications involving only a few pairs. In high-capacity, long-distance applications, however, the relative cost is very high. Applications. Generally speaking, UDP is no longer deployed in long-haul outside plant transmission systems. Coaxial cable. Coaxial cable is a very robust shielded copper cable. The center conductor is much thicker than a twisted pair conductor and is surrounded by an outer shield/conductor that serves to greatly improve signal strength and integrity. A layer of dielectric material, either foam or solid, generally separates the two conductors. The entire cable is then protected by another layer of dielectric material. The two conductors share a common axis, hence the term coaxial. Bandwidth. The effective capacity of coax cable depends on the gauge of the center conductor, the nature of the dielectric insulation, the length of the circuit, and the spacing of amplifiers and other intermediate devices. Error performance. Coax offers excellent error performance due to the outer shielding. As a result, coax was used extensively in classic data application. But the end-to-end integrity of the shield is crucial. Either physical damage or poor splicing will result in awful error performance. The shield also must be grounded properly. Distance. Coax does not have the same distance limitations as either UTP or STP, because the thicker center conductor offers less resistance to the signal. Nonetheless, amplifiers or other intermediate devices must be placed at appropriate intervals to extend high-frequency transmissions over significant distances. Security. Coax is inherently quite secure as it is relatively difficult to place physical taps on coax without detection. Little energy is radiated through the outer shield, so radio antennas and inductive coils are of little use in gaining access to the raw signal. Cost. The acquisition, deployment, and rearrangement costs of coax are very high compared with UDP due to increased bulk and weight applications. The superior performance characteristics of coax favored its use in many short-haul, bandwidth-intensive data applications. Current and continuing applications include host-to-host, cabinet-to-cabinet, microwave radio, a form of radio transmission that uses ultra-high frequencies. Bandwidth. Microwave systems offer substantial bandwidth. The issue of overall bandwidth availability is determined not solely by the spectrum allocated for microwave used by the regulatory authority, but also by the fact that spectrum is licensed to users on a geographic basis. Error performance. Physical obstructions must be avoided at all costs, as even grazing the smallest obstructions has a decidedly negative impact on error signal strength. Microwave radio also is particularly susceptible to environmental interference. Distance. Microwave clearly is distance limited, especially at the higher frequencies. Distance limitations can be mitigated through larger antennas and antenna arrays incorporating spatial diversity and frequency diversity to increase the quality of the collected signal. Security. As is the case with all radio systems, microwave is inherently insecure. The radio antenna tuned to the proper frequency range and positioned in proximity to the microwave path can easily capture the raw signal. Security is imposed through signal encryption. Cost. The acquisition, deployment, and rearrangement costs of microwave can be high. Applications. Microwave historically has been used extensively for long-haul voice and data communications. Contemporary microwave applications include long-haul carrier networks, private networks, carrier bypass, disaster recovery, interconnection of cellular radio switches, and WLL. Satellite radio. Satellite radio is a microwave transmission system utilizing non-terrestrial relay stations positioned in space, where there is no atmosphere and certainly no ether. Bandwidth. Satellites can support multiple transponders and, therefore, substantial bandwidth. Error performance. Satellite transmission is susceptible to environmental interference. Error performance also is sensitive to the proximity of the Earth stations to the equator, and to the physical location of the receiving antenna within its footprint. Distance. Satellite, generally speaking, is not considered to be distance limited, as the signal largely travels through the vacuum of space. Security. As is the case with all microwave and other radio systems, satellite transmission is inherently insecure. Satellite transmission is especially vulnerable to interception, as the signal is broadcast over the entire area of the footprint. Cost. The acquisition, deployment, and rearrangement costs of the space segment of satellite systems are quite high, easily $200 million, including the satellite and its launching. But a large number of user networks can share the satellite. Applications. Traditional and still viable applications include international voice and data, remote voice and data, television and radio broadcast, maritime navigation, video conferencing, transaction processing, inventory management and control, and paging. More recent and emerging applications include air navigation, GPS, mobile voice and data, fiber optics. Conventional fiber optic transmission systems optoelectric in nature. The signal originates as an electrical signal which is translated into an optical signal which subsequently is reconverted into an electrical signal at the receiving end. Bandwidth. Fiber offers by far the greatest bandwidth of any transmission system, often in excess of 2.5 gigabytes per second in long-haul carrier networks. Error performance. The optical signal suffers from attenuation and distortion as it traverses the fiber. Distance. Single-mode fiber optic systems are routinely capable of transmitting unrepeated signals over distances well in excess of 600 miles. As a result, relatively few optical repeaters are required in a long-haul system, thereby both reducing costs and eliminating points of potential failure or performance degradation. Security. Fiber is intrinsically secure because it is virtually impossible to place a physical tap without detection. Cost. While the acquisition, deployment, and rearrangement costs of fiber are relatively high,
Created using Powtoon.